Hello, my name is David, and I will be working with Enrique, Jorge, and Ricardo on the thermodynamics of black holes. Now, before my peers could delve into where the modern research and ideas of black holes are today, I will be introducing the early theoretical foundations of black holes. To begin, I'm going to start with the Einstein field equations, and this equation predicted the existence of black holes, and it provides a framework for the understanding of their properties. This equation describes how matter and energy curve spacetime, and how this curvature affects the motions of matter and light. And we can see the formula right here on the right and what the units mean on the left. Following this, we have the Schwarzschild solution. And this was a solution to Einstein's field equation, as it tells us about how black holes behave in the simplest case, this being a non rotating, uncharged spherical symmetric mass, assumed in a vacuum, meaning there's no matter outside the black hole. This solution describes the spacetime geometry outside any spherical mass. Yet, when the mass is concentrated within a critical radius known as the Schwarzschild radius, seen in the bottom right here, it forms what we know as a black hole. And the surface of the black hole is known as the event horizon. Anything crossing this boundary could never return or send any signals out. There are also other things this equation tells you, like the singularity and that black holes are described by their mass only. Cool little fact, this equation also tells us how time and space behave strangely near the black hole, as time slows down as you approach the event horizon, as light is redshifted to lower energies. This weird behavior is a result of the extreme space-time curvature as seen right here. Now, drawing it back to how the solution says that black holes are completely described by their mass. Why do we care? Well, this kind of throws in a thermodynamic paradox. Yet, before I could get into the paradox, I must explain what we do know. One of these being the third law of thermodynamics, which states that as a system temperature approaches absolute zero Kelvin, its entropy approaches a minimum value. We are also aware that an entropy of an isolated system can never decrease, or will always increase, the second law of thermodynamics. What's weird about how black holes only being described by its mass is that there's no rotation or charge, implying that black holes have no internal distinguishable features from the outside. This, followed by the null theorem, which is inspired by the Schwarzschild solution, where the null theorem states that once a black hole forms, its entire description is described by three external parameters: the mass, the charge, and the angular momentum. All other information is lost to the external observer. What does this all mean? What does this tell us about black holes? Well, back then, they had the thought that classical black holes had no entropy, they don't emit any radiation, they can only reduce observable entropy. This leads to questions as, if you were to drop something into a black hole that has entropy, how is it that this entropy just completely disappears? These were the initial thoughts up into 1973, where Jacob Bekenstein, this amazing Mexican American physicist, proposed that black holes have entropy. And he proposed that black holes must have entropy in order to preserve the second law of thermodynamics. He argued that the event horizon should be proportional to the entropy, where the black hole entropy is not volume dependent, but rather proportional to the surface area. Following this proposition, he introduced the generalized second law. And sadly, he didn't just wake up one day. I was like, yeah, this makes sense. Let me roll with it. He actually had an experiment planned and essentially math to back up his theory. To begin, his experiment was imagining a small box that it has mass, energy, a certain radius, and entropy. This box is slowly being lowered into the horizon of the black hole, where the end goal is to ensure that the entropy loss when the box crosses the event horizon is compensated by the area increase of the black hole. And as you can see my little diagram, where you have a box entering the event horizon, and here in the bottom is the generalized second law pre-Hawking. This takes us to this equation here, where essentially we imagine a small box, or we imagine the box as it approaches the event horizon, and the energy that actually crosses the horizon is redshifted, meaning that the effective energy is added to the black hole is reduced. Near this horizon, the minimum energy the box can deliver is approximately this, where m is the mass of the box and phi is the gravitational redshift of the factor. Yet, Bekenstein also included this for tight bounds. He realized that the minimum energy required to cross the horizon will be dependent on the size of the system, leading us to this second formula in the top right, the minimum energy condition. This formula is based on the fact that compressing the box to a certain degree or too much will actually cause it to collapse into the black hole, setting a lower bound on the energy required to push the box across the horizon. Taking all this into mind, he had to do an entropy area relationship, where this leads us to the Schwarzschild radius and the area of the event horizon, where as you can see here in the bottom left, he combined the two. where g is the gravitational constant, m is the black hole mass, and c is the speed of light. Next, he considered adding a small amount of energy, or mass, which is dm, which is seen here in the bottom right, to the black hole. And in order to add this, you could just deviate the a from the previous formula, allowing you to plug in dm. Following this, it allows us to plug in the minimal energy condition, which allowed Bacon-Sand to argue that the minimum energy required to add mass to the black hole will lower as you approach the event horizon. After simplifying, this leads us to the final form of the area change relation. Now, if we were to treat this as a general result for any mass added near the horizon, we get what Bacon-Sand used, which is this formula right here, the entropy area relationship, where E is the energy added and R is the characteristic size of the object. And again, here we have the generalized second law pre-Hawking, where delta SPH is the entropy gain of the black hole proportional to delta A, and delta S outside is the entropy loss to the external system. What does this all mean? Even if the external entropy decreases, like if something were to fall into the black hole's own horizon must increase in order to compensate, keeping the total entropy non-decreasing. This relationship preserves the second law, even when entropy crosses the event horizon. Yet, we must keep in mind that Bacon-Sand introduced a new idea that black holes must have entropy, and the thermodynamic behaviors mirrors the familiar laws of heat, energy, and disorder, proposing that entropy is proportional to the surface area and the black hole's event horizon. Yet, this was all theoretical. As mentioned before, black holes were still thought to be completely cold and incapable of radiating anything. This leads us to Jorge on his section of.
Hi, my name is Jorge Navarro, and today I'll be talking about Hawking radiation and the black hole entropy. So the first thing I'll talk about is Jackie Bekenstein. He introduced black holes as a new source of entropy for the universe. He actually proposed that entropy in the black holes is proportional to its surface area, as seen here. He actually got this from this equation right here, which is the first law of black holes, where K is equal to the surface gravity, A is equal to the area, omega is equal to angular frequency of rotation, and phi is equal to the potential of the event horizon. And if we actually substitute mc squared for energy as an Einstein model, we'll see that this actually looks very familiar. It actually looks a lot like the fundamental equation for energy. And this is where this proportionality comes from, as here's a change of entropy, and here's a change in area, where k is a scalar for the black hole model. And according to classical thermodynamics, if black holes have entropy, then they should have a temperature, as seen here by the definition of entropy, where the change in entropy is equal to the change in heat divided by temperature. But if they have a temperature, then they should emit radiation, should not be black at all. And this was actually Stephen Hawking's argument whenever he tried to prove Bekenstein's theories wrong. But by using a semi-classical model with quantum mechanical effects, he actually found that this actually has a temperature. And he did this by taking the first law of thermodynamics, where the change in energy is equal to the change in heat plus the change of work, setting the change of work to the surroundings equal to zero, and then taking the definition of entropy, solving for the change in heat and plugging it back to the equation, and solving for temperature, you get temperature is equal to the change in energy with respect to entropy. And right here, for the energy, we substitute E equals mc squared as an Einstein's model to get temperature is equal to the change in mass times, no, change in mass with respect to entropy times the speed of light squared. And if we take the inverse of that, we take a temperature is equal to the speed of light squared with the change of entropy with respect to mass. And we could find this by taking Stephen Hawking's entropy model and multiplying it by the area of the event horizon, where we get entropy is equal to 4 pi times Boltzmann's constant times gravitational constant times mass squared over h bar times speed of light. And if we take the derivative with respect to mass of this, we get ds dm is equal to 8 pi times Boltzmann's constant times gravitational constant times mass over h bar times the speed of light. Taking this and plugging it back into what we solved over here inversely gives us that temperature of a black hole is equal to h bar times speed of light cubed over 8 pi times Boltzmann constant times gravitational constant times mass. This is actually known as the Hawking temperature. And this is especially important because this is actually the temperature that the black holes radiate energy out of. But what's strange about this is when you look at this, temperature is inversely proportional to mass. So that means that whenever mass is actually lower, that means that heat increases, which is kind of strange. We don't see that. We usually see the opposite. Just something to keep in mind. So if we define Hawking temperatures, TH, we can define TM as the temperature of matter and radiation outside of black holes. So whenever TM is greater than TH, a black hole accretes outgoing radiation, and temperatures means it's pulling stuff in, which higher the entropy of the black hole. Whereas as TM is less than TH, the black hole emits Hawking radiation and lowers the entropy of the black hole. So looking at this right here, it'd be radiating out at all times like that. But this is only true if the temperature outside of the black hole is less than the temperature of the black hole, following the second law of thermodynamics. As the universe expands, it'll keep expanding until eventually there's not enough entropy, and the entropy of the black hole will start going from a place of potential to the final of the maximum. Finally, according to Einstein's model, E equals mc squared, when a black hole emits radiation, it is essentially losing mass. So, like I said, they will evaporate over that time. And the final findings of Stephen Hawking for this was actually the simplified version, where the temperature is equal to K over 2 pi, where K is equal to surface gravity, and the entropy is calculated as 1/4 over area. And that is the end for me.
Black hole chemistry, also known as the extended black hole thermodynamics, applies thermodynamic concepts to black holes. Understanding black hole chemistry is valuable information since it allows researchers to study the behavior of black holes and provides insights into the physics of black holes as well. Research into black hole chemistry right now is focused on holographic black hole chemistry, observing the mass of black hole through the enthalpy of black holes and the phase transition of black holes. Current information on black hole chemistry includes the extended first law of thermodynamics and the phase shift properties of black holes. Both of the topics that will be discussed about black hole chemistry will have some relation to what was learned in class. First, the extended first law of thermodynamics and its relation to black holes. The first law of thermodynamics, also known as the conservation of energy, is energy cannot be created or destroyed, but transformed from one form to another. The first law of thermodynamics refers to change in internal energy. If the internal energy increases in a system, then the energy of the surroundings decreases, and the heat and work put into the system is greater than the heat and work put out of the system. The same applies when internal energy decreases and the energy of the surroundings increases. The same law applies to black hole chemistry, as we treat it as a thermodynamic system. The black hole's event horizon, which is analogous to entropy as explained before, the variables given are related to it: mass, angular momentum, electric charge, and surface gravity. Surface gravity is interpreted as temperature and the mass of energy of a black hole. As seen in the slide, the two equations were derived from the first law of thermodynamics. The first one is derived from the first law of thermodynamics based on the system's internal energy, which change in internal energy is equal to the change in heat plus the change in work. While the extended first law is change in enthalpy is equal to the change to temperature times the change in entropy plus volume times the change in pressure. Black hole changes in enthalpy can identify the changes in mass, which is what the first law of thermodynamics applies for black holes, rather than changes in internal energies as the first law normally does. Using the extended first law of thermodynamics, researchers can understand black hole properties such as mass through a thermodynamic viewpoint. Now moving on to the next topic. Phase shifts, also known as phase transitions, in thermodynamics is when a substance changes from one form of matter to another, such as liquid water to frozen solid ice. The changes happen due to changes in temperature and pressure. Using the Clausius-Clairain equation learned in Chapter 19, the equation relates the pressure of a substance and the heat of a vaporization to determine the energy required to change one phases from one to another. Normally used to describe changes from liquid to gas, but in terms of black holes, the phase changes regarding the size of black holes, going from large black holes to small black holes. Also, this process usually describes ADS black holes. As seen in the graph, the one on the left, this slope describes the Boolean equilibrium of a phase transition from a liquid to a gas. How changes in temperature and pressure mean a change in the current state of matter, such as water turning into vapor. The graph on the right is the equivalent graph for black holes, but instead of phase changes from liquid to gas, into small and large black holes. Changes in pressure and temperature can cause a phase change, but as seen in the graph, the slope does not go all the way since it reaches a critical point and changes end. Further research is being done to understand why the critical point happens and what happens after it. Understanding phase changes in a black hole in terms of thermodynamics can help researchers link black hole thermodynamics to the ideas of van der Waals fluids and triple points, which can help understand the behavior of black holes. Black hole chemistry is an extension of black hole thermodynamics as it helps understand the structure and formation of black holes, with research being covering black hole entropy via statistical mechanical interpretations.
My name is Enrique, and I will be covering a little on some modern research on black holes using statistical mechanics interpretations. So, black holes are very mysterious, but as mysterious as they are, we can still describe their entropy the same way we understand heat in everyday objects. And first, we just need to understand a little bit about statistical mechanics. So, in statistical mechanics, entropy measures the number of ways a system's parts can be arranged while still looking the same, these parts being molecules and atoms. And so essentially, statistical mechanics bridges the gaps between the microscopic and the macroscopic. And this idea is encoded in Boltzmann's formula, where omega is the number of accessible microstates. And black holes, as it turns out, do have entropy, as described earlier in the Hawking-Braystein equation, where they show that a black hole's entropy is proportional, not to its volume, but to the area of its horizon. But how does statistical mechanics correlate to black hole entropy? Well, a key concept in statistical mechanics is ensembles, which is a collection of all the microstates, and this is used to describe systems at different conditions. Two of the main ensembles include the microcanonical ensemble, which describes a system with fixed energy, and the canonical ensemble, which is a system with fixed temperature, especially another one when it comes to black holes, which will be mentioned later. But how does what does this mean for black holes as thermodynamic systems? Well, for black holes, we don't know all the quantum microstates, as we know they're still an anomaly, but we do know their macroscopic properties like mass, angular momentum, and even temperature. So statistical ensembles can give us an interpretation of black hole entropy. And we can get some information from the paper called the Statistical Ensemble and Logarithmic Corrections to Black Hole Entropy by physicist Aritra Ghosh, who uses thermodynamics and heat flow to understand black hole entropy. Here, entropy is linked to fluctuations like small changes in energy or volume, and it all depends on the ensemble we use. So when a black hole exchanges energy with its surroundings, even tiny thermal fluctuations increase the number of microstates, which leads to logarithmic corrections in his equations, like right here where C means specific heat. So this approach doesn't rely on knowing the microstates. Ghosh shows the entropy corrections can be shown just through thermodynamic principles. So if we know how the black hole exchanges energy, volume, and charge with the surroundings, then we can determine its corrected entropy. Ghosh's paper also explores a modern framework called black hole chemistry, where the cosmological constant A is treated as pressure and the mass of the black hole becomes enthalpy. And in that context, the natural ensemble is isoenthalpic isobaric, where the enthalpy and pressure are fixed. This shift leads to different entropy corrections, not because the law was changed, but because the system is now in a new environment and you don't want to misinterpret thermodynamics. So by interpreting black holes through statistical mechanics, we see entropy as a measure of the system's microstates. But Ghosh's work and the framework of black hole chemistry shows us something deeper. Whether we count microstates or analyze heat flow, entropy gives us a window into the hidden structure of black holes. Thank you for watching our video. This was our presentation on the thermodynamics of black holes.